Hey guys, and welcome back to the Academy. So what we're working on now, we're going to build on our password protected ticket project. If you haven't already, just make sure, if you're following along at home, just go ahead and download this from our GitHub repo so you can follow along. But what we're working on here now is the importance of converting our strings to bytes 32. Now, what you might not realize is strings are actually very, they're not as efficient to store. And if you've ever come up against the limit, blockchains have a limit on how many bytes can actually be stored. It's like 24,000 something or like that. And I've had pretty bulky contracts that have gone up to that point. There are going to be times where every byte counts, right? And you also don't want to ever make it super expensive for your client to manipulate those strings, or for people who are going to be minting from the contract to store those strings. So if we had a situation where, for this particular project, if we had a setup where, let's say, a person could mint a ticket. In this example, what we're doing is a person mints a ticket and they're given a secret password. And that password is something that they have to deliver upon entry into this special event. That's kind of the whole point of, like, okay, it's a password protected ticket, right? And so what we're going to be working on is building that redeemer struct, we're going to call it, and setting it up where a person can store this password, this secret password, and only the owner of this contract is going to be able to read this password, and they'll be able to say yes or no, you can enter, and it depends on, if they have the correct password. Only the owner is going to know this password. So that's kind of the point. And the issue, though, is as this list gets bigger, as this array of redeemers gets bigger, this is going to be much more expensive. It's going to make the contract a lot less efficient. So that's the whole purpose behind us making something where a person has to, or when a person actually goes to mint, let's see what it says. When a person actually goes to mint and they have to redeem their ticket with this little claim ticket item, it's going to be a little bit cheaper to do so, right? So let's hop into that. So a couple things that we want to do first, just to clean things up a little bit. We want to make sure that we have our URI function. This is actually one of the most important functions. And we're overriding the URI function that comes with ERC 1155. That's the necessity for that. I'm going to return. And what this does right here is we are going to cast basically what we get from the ABI with this special function encode packed. What it's doing is what it's saying is we want you to concatenate or smush together the base URI we are going to use the library strings, which is all the way up here. It's our special library that handles certain special input values or parameters that we take in. We are going to use that. And where was I? ToString token ID, which in this case is a uint 256. And add it to this JSON extension. So basically it's just concatenating all of this, everything that's separated by a comma. And I believe I need one more, maybe. What's up? Bam, that's why. All right, great. Okay, good. So now what we're going to do is also, let me add the set URI function while I've got it. This is if you want to change the URI. Okay, perfect. So now, the mint function is actually pretty easy. If we were to do something like the mint here, what we're gonna do, what's this error? Oh, whoops, so we missed something. What we wanna put in, this is something that Open Zeppelin didn't say actually. It's this. You have to specify what it's overriding or the error doesn't go away. So that's what it's saying. So we go from here, let's add our mint function. All we need is the number of tokens, external, payable. Payable if you're accepting only the native token and not like a token of your own, like an ERC20. And that's literally it. So what we need to do though is when a person mints, what this is saying is use this internal function that's borrowed from ERC 1155. You're going to mint to the sender, the person who's calling this function, the token ID, which is just 1, and the number that they are minting. And then this last parameter is for data. We need to put this in, but we can just leave that blank. What we need to do though is the interesting part happens when a person goes to redeem, right? So let's go back up to the top, and what we're going to build is something called a struct. So what the struct looks like is going to be something like this. Redeemer. And we're going to store the address for the holder and the data. Whatever that data is, whatever the password you decide to set for the person. Okay? And then from that, we actually need one more thing. We will create a mapping called redeem tickets. This is going to make more sense to what this does in a second. Okay, so the very first thing we want to do is we want to be able to convert that data. So let's do it this way, because this is going to be a little bit more complex. When a person goes to claim the ticket, it's pretty straightforward. What it's going to do is we're going to have a person claim the ticket, and they're going to input some data. They're going to input whatever password you specify they need to give you. And from there, what we're going to do is we're going to set our require statements for what we need to check. We're going to then, lastly, what we're going to do is we're going to update our states and burn the ticket. And this little middle step is the more complicated step. This is where we have to convert that data that they give us. They're giving us data in string format. Convert string to bytes 32 to make it cheaper to store. Okay? So just to kind of break the function up that way. So what we're going to do is value shit funds for claim. Just check to make sure they paid the right price. If you want to charge them to claim, you can, or you don't have to. Balance of, again, is a function that comes with ERC 1155. And that's it for that. So those are the required statements that you need. Next, what you need is to set the type for the data. And then we're going to do this cast thing again. So you're going to cast it to encode packed. Data. Okay, and what I just did here is this is your mapping. So when we go back up here for our mapping, all this is doing is, okay, for this mapping at this position that I'm putting in, create a new redeemer struct. Got it? So when I create a new redeemer struct, it just looks like this. Redeemer in parentheses data, right? So what is this saying? We know that for a redeemer struct, it takes in an address and it takes in whatever data that it gives you. But before we do that, we have to convert that data, because a person could give us, a really long string, or it could be more expensive as a string than it would be for bytes 32. And really that's it. So when I say update our state, all I mean is the count has to be updated. So you see that by updating the state, once we increment by 1, the count in the total tickets claimed is going to go up by 1. And so the next time the ticket is claimed, the next position is filled in. So that's how this mapping works. You have a number, and then every time a ticket is claimed, it just increments by 1. So count 1 has a redeemed address. Count 2 has a redeemed address. And it's storing all of this data as it goes along. And then the last thing, we have a burn function here. Ticket 1, bam. Okay, so there was a lot to do here, but basically what you're doing is you're just checking to make sure a person can, so they don't waste their gas trying. And then you are casting this data, the string data that you gave them, to Bytes32 to make it easier to store. Now, how do we read all of this stuff? Basically, the way we read it is like this. So what we're gonna do is convert everything back. So we want to use a function that allows the owner only to check and make sure that the value that you gave lines up. And one of the nice updates, especially with, I know this works for Etherscan for certain, but Etherscan allows you, if you go to the read contract section, to add a modifier like only owner, where you have to connect your wallet, and if you are not the owner, there are certain functions that you can gate them and still make them private. So that's how you would do that. Converted. So what are we doing here? We are going to convert this back to a human readable string. So we stored it as a cheaper Bytes32. And when the owner goes back to read it, they're not going to be able to read Bytes32. So what we need to do is make it human readable, so we convert it back to a string. And then return it. All right, so that's basically it. It might not seem like a lot, especially if you are just doing this through a test network and just kind of learning for now. But trust me, when you get to doing something like deploying for an actual project where gas efficiency becomes an issue, you're going to want to make sure that you're doing everything to optimize that contract. And for that, kind of understanding how much it costs to store strings versus bytes. This is also a thing when it comes to Merkle trees and that type of thing. The importance becomes pretty evident when the contract gets a little bit more complex. So understanding those data types and variable types is going to, in my opinion, take you from that beginner level up to the intermediate to advanced level, if you can master them well. So to wrap things up, let's go ahead and run this application, or deploy this contract, I should say rather. So in Remix, again, it's just super simple this way. We can just keep it in Remix VM. But what we're gonna do is just go, we can just call it test URI, whatever we want, deploy it, and let's submit 10 of them. Was there a price? Did I set a price? I don't think so. Okay, perfect. So we went ahead and minted. And if I wanted to go and, well, let's check a couple things. So count should be 0. Soulbound is on. If I wanted to, let's go ahead and check Soulbound real quick, actually. So in a different wallet, let's go ahead and ownable caller's not the owner. Oh, quick issue. In this particular example that I used, it's not for, it was actually for the owner to distribute these tokens. So what I would do instead is I would be transferring them to people. Again, it kind of depends on how you run your mint. This particular example, it was for the owner or the purveyor of these tickets to distribute them how they saw fit, which you can do as well. But just for purposes of this tutorial, I'm going to show you how to do that. So if I was to transfer to the second address, let's safe transfer from. ID 1, let's send them 2, and I think I can just do that. And then my address. No, it has to be 0 in remix. Or it has to be nothing. Oh, okay. So one quick distinction for remix, for whatever reason, for data, it's gonna get finicky and you have to put in like a empty array. So just the square brackets, I guess, works fine. On a front end, you wouldn't have to really worry about that too much. But okay, so I went ahead and I transferred. Now let's go ahead and see if that soulbound is working. So what we're gonna do is we're going to take this third address and we're gonna see if we can transfer. So we're gonna go from that one, from wallet 2 to this third wallet, and let's see if it works. It shouldn't work. Okay, and from there you see that, okay, soulbound token can only burn or return to token owner. So that's what we want. That's what soulbound is. Now from there, what we're gonna do is let's change the 2 to the owner. And then let's only send 1 back. And so you see that it works. So when it's soulbound, you can only send it back to the owner. Technically, you can also burn it. But in this instance, we see that it's working just fine. Let's go ahead and try to claim our ticket with our super secret password that we deliver. And then you see that it works. Okay. So with that, in a second, I'm going to show you what the owner is going to see. But because I only have 1 in my possession, let's just make sure that it doesn't work the second time. Okay, so we were down to one ticket, and you see that no ticket could be redeemed. So what can the owner see when they go to read info? The owner can go ahead and, if you're following along with the full copy or the full contract, there is a read all function that just pulls everything up. But if I wanted to check, I think the count would be 0. And you see their super secret password pops up, right? And then read all, I could get the address and I can get super secret password from that. And that's just in the full version. There's this additional list that we build. You can go ahead and check it out. It's in the GitHub repository. And that just gives you a full list of the address attached to the data that you've added. So it converts that bytes to the string, so it's easy for me to read. But yeah, as we can see, everything works just fine the way we want to. We've got soulbound. We are converting our data to make it more optimized. And we're burning the tickets as people are entering our super secret special Web3 boxing event. So everything works just as we intended. All right. See you guys in the next lesson.